been on extremely firm ground the entire way. Now, I may not always have been able to make things 100% clear to you, but that's my failing. It's not in the science. From here on out, we're going to start talking about things that are less well understood. I'm going to be talking about experiments that don't have good explanations. I'm going to be talking about theories that aren't verified. I'm going to be talking about crazy ideas that some guy had once upon a time. It's all going to be a lot more speculative. So I want to say that right off the bat before I start, that you should really, think of everything that I've said up until now is pretty solidly understood and accepted. From here on out, there's a lot more room for debate. So today's lecture is supposed to be string theory, a different kind of unification. I want to remind you all where we stood last week before I move on. This is the Higgs mechanism the Higgs particle is the particle that binds together the weak force with the electromagnetic force, and also explains how quarks and the weak mediators obtain mass. We talked about the fact that the weak force is different from the strong and the electromagnetic forces because the mediators are massive and because they carry charge, which means the weak mediators interact directly with the electromagnetic mediators. And this is, different from the strong and the electromagnetic forces. Then I talked about this picture we have of particles being disturbances in some field. I had the analogy of a rubber sheet. And the rubber sheet is stretched out, and a particle is like a little bump in it that travels, a little wave. And because of the elasticity of the rubber sheet, this bump requires energy to disturb the rubber sheet. And that energy is the mass of the particle. And as it travels along, it also has kinetic energy. Then we talked about what a symmetry was and the idea that there might be a symmetry of the laws of nature, like, for example, the fact that Newton's laws work just as well here as they do in New York. That's a translation symmetry that isn't actually realized in the real world because we know that Chicago isn't the same as New York. And I talked about the idea that the Higgs field is a particle, is a field that has a potential energy with this double well shape. And because of that, it has the potential itself has a symmetry, but in the actual physical vacuum, the Higgs field settles into one well or the other, and at this point, that underlying symmetry is broken in the real world. And that symmetry ends up also breaking the symmetry between the electromagnetic force and the weak force. And whereas you started probably with 4 mediators that were all basically the same, afterwards you have the photon on the one hand and the 3 weak mediators on the other. And furthermore, because what we call the vacuum is actually the field is at some finite value, the Higgs field is just some finite value everywhere, particles that interact with the Higgs field as they travel through the vacuum, there's an energy associated with this interaction that becomes an effective, what we see as a mass for that particle. It has some inherent energy just from being in what we call the vacuum. And that basically explains how the Higgs particle both splits the electromagnetic and the weak forces into 2 things and gives masses to everything around us. Now, come on. Like I said, when I planned this lecture series, I planned to introduce string theory today as a different way of unifying forces and particles. That was my idea. I sat down this week to write this lecture, and I got about halfway through, and I realized I had actually written a different lecture. I had more questions than I had answers. And after a certain amount of time and struggling with it, I decided that questions in it that I don't necessarily have the answers to. And I will talk about string theory and introduce it, but perhaps a more appropriate title for the lecture is The Trouble with Gravity. So let's talk about gravity. It's a funny thing. Gravity is probably the oldest force that we've understood in a scientific way. It's the force that Newton worked with all the way back in the 17th century. It's the first force that we really wrote down mathematically. And yet, it's the one that we still feel like we don't understand. And why is that? Well, okay. Most of us probably have heard that what determines how much two particles or two objects gravitationally attract is how much mass each has. The mass of an object determines how much it is affected by gravity. And in particular, an object of some mass m in a gravitational field G feels a force F equals mg. More mass, more force on it. Linear relationship. Now, so far, doesn't look all that strange. It's actually quite similar to electromagnetism. In electromagnetism, the charge of an object determines how strongly it feels the force of an electromagnetic field. If the electric field is E, then the force is F equals QE. Again, more charge, more force. So far, it doesn't really seem all that different. But the thing about mass is that it plays a second role in physics. And that the role that it plays that makes it special is that it also determines how much acceleration an object undergoes because of some force. So if an object has mass m, when it feels a force F, the acceleration it undergoes is F equals ma. And the thing is that mass appears in both of these places, and this one is really special. And this sets gravity apart, because if you take an object in a gravitational field, what you find is that the acceleration it experiences is independent of its mass, because you have F equals ma equals mg, and the masses cancel out, and the acceleration is the same no matter what the mass of the particle is. This doesn't happen in electromagnetism, because you can have particles, you can change the charge of the particle without changing the mass, or vice versa. Now, physicists, when they talk about this, they refer to the m that appears in F equals ma as inertial mass, the amount of stuff that drags, that tends to resist acceleration. And they refer to the m that appears in F equals mg as gravitational mass. And what we say when we want to describe this is that inertial mass is the same as gravitational mass. And the interesting thing is, this probably seems like I'm belaboring a very minor point here, but actually physicists have spent a significant amount of time doing precision measurements to establish this equality. And nobody has ever found any difference in any object between the inertial mass and the gravitational mass. It's just one number. And it has very, very deep implications. So there's a thought experiment due to Einstein that I think he actually set in an elevator, because he didn't set things in spaceships. But I like spaceships, so I use them. Suppose we have a guy in empty space, so there's no gravitational fields around, and he's inside a rocket, and the rocket is accelerating in some direction. If you're inside the rocket, and there's no, all you notice is that it feels like you're being pushed against the back of the rocket. The rocket is accelerating this way. I mean, we've all felt this in a car, right? The car accelerates forward. We feel pushed back against the back of the seat. In this perfect scenario, the guy inside the rocket, all he feels is like he's attached to the bottom of the rocket. There is no difference between this feeling and the feeling of being in a gravitational field. I'm attached to the ground right now. I feel exactly the same thing. actually in a gravitational field or whether he is accelerating in empty space. And if there is no experiment that you can do that tells the difference, then there isn't a physical difference. The two are the same to all scientific intents and purposes. This is at the core of general relativity. And what it means is that we can stop thinking about the gravitational force as we have a mass here, and we have a mass here, and this thing is attracted to this, and we use F equals mg, and we use F equals ma, and we come up with an answer. Instead, you can basically absorb the effects of gravity into the background. I'm going to use the blackboard a little bit more than usual today. Here's a mass being attracted to a mass, and he starts to move with greater and greater acceleration. This picture is indistinguishable from he just falls down a hill. If you sort of think about his velocity in this direction, and because no matter what object you put here, it'll always accelerate in the same way, you don't need to think in this picture. You can just absorb it all into the background, and it becomes just, space itself is curved. And that's the main implication of general relativity, and the reason it works, again, is because of this relationship up here. Now, you may recall that in the first two lectures in the first lecture I introduced the speed of light, and I said, when speeds are small compared to the speed of light, we have no real special relativistic effects. But when speeds approach the speed of light, you have to take into account special relativity. So over here is the classical Newtonian world, and as I increase the speed, I wind up in a special relativistic world. And then in the second lecture, I introduced Planck's constant, which sets the scale for when quantum mechanical effects take place. And I said, well, if you study the world at reasonably large scales, then you're basically in a Newtonian world. But as we start studying smaller and smaller objects, if we decrease the size in comparison to Planck's constant, then we have to take into account quantum mechanics. And there in the back corner of the cube where you can't see it is the world where quantum mechanics live. And if you have to do both, if you're studying particles that travel at very high speeds and are very small, then you're over here. And that, as I mentioned, is the world of particle physics where we have lived for the last 4 weeks or so. Now I have a third number. Newton's constant g, which appears in the universal law of gravitation, sets the scale of gravity. It determines the strength of gravitational effects, and that determines where general relativistic effects become important. If you're talking about a situation where there's not enough mass to curve the universe very much, then you're basically in a Newtonian world still. You're down here on the plane. In this world, this is, our solar system, for example, the mass of the sun and the mass of Jupiter and the mass of the Earth and whatnot, these are not really enough to have huge general relativistic effects. But as you increase the amount of mass in comparison to this number g, you wind up on the top of this cube where general relativistic effects become important. And in particular, we would normally consider traditional general relativity a regime where we both have to take into account special relativity and the effects of gravity. So that lives over here in this corner. And where we would like to get is over here, where we can take into account all three effects, where we're in a world where we have general relativity and we have quantum mechanics and we have objects moving fast near the speed of light. So this is where we want to get. The second thing about these three numbers is that together For example, Planck's length is a particular combination of these three natural numbers. And what's important about these natural scales is that when you reach this natural scale, you're up here. If I'm talking about lengths that are on the order of Planck length, if I'm studying the universe at this distance scale, then I'm definitely up here. I have to take into account all of these effects. So they create a framework of when all of these things become important. Now, I'm sure most of you have heard of this. Black holes are possibly one of the most famous predictions of general relativity. Suppose you start with the mass. In the Newtonian picture, you have this mass here, and you have this gravitational field. And point particles in it curve around. They tend to fall towards the mass, or if they start out moving a little bit away, they curve inward. This is the old picture. We replace it with this picture where space is curved, where it sort of becomes a funnel picture, and these masses just sort of travel in the curved space background. And you see that if you picture the mass as some point mass at the center, then this curvature picture seems to have an issue right here. It seems to curve space so much that it gets weird and singular and we don't know what happens. When mass is concentrated, now usually in the physical universe, you don't have a point mass. What you have is the sun. And the sun is very massive, but that mass is spread out over some volume of space. And so if you actually approached the sun and managed to get inside it, what you would see would be some smoothing out of this picture because the mass isn't focused right there at the center. But when enough mass is concentrated in a small enough region of space, what you create is this kind of weird singularity, and this is called a black hole. One of the most important aspects of a black hole is the horizon. At some distance, r, which depends on Newton's constant, the mass of the object, and the speed of light, there is a horizon, and I split that equation awkwardly. But the main point here is that the larger the black hole is, the further out its horizon is, and the smaller the black hole is, the closer in its horizon is. Now, I just mentioned to you that the sun, although it is a very massive object, is not a black hole. What determines whether or not an object is a black hole is not how massive it is, but how dense its mass is. A black hole can actually be very, very light, but if that mass is concentrated in a small enough region of space, then you have a black hole anyways. And what do I exactly mean by small enough region of space? What I mean is if this amount of mass is inside this radius, if all of the mass needed is inside this horizon, then I have a black hole. In the case of the sun, it would have to shrink, that amount of mass would have to shrink by quite a bit into a much, much smaller object to get all of that mass inside the horizon, and then the sun would be a black hole. But that, for our sun, will never happen. Once you have this horizon, the horizon is like a one-way gate. Objects can pass inward towards the black hole, but they can't pass outward. Nothing, not even light, can escape a black hole. And by escape a black hole, I really mean cross outward past the horizon. Now, for those of you who like science fiction movies, there are a great many very inaccurate images of black holes out there. And something calamitous always seems to happen when you cross the horizon of a black hole. This, it turns out, is a total myth. Locally, the horizon doesn't actually horizon is, the more locally the horizon just looks very close to being flat and normal and ordinary. If you crossed a horizon, you wouldn't notice necessarily. It's not like suddenly a flash of light occurs and I don't know, you turn into your evil twin or something. Nothing strange happens at all. And even if you tried to go back out, you wouldn't notice that you hadn't. It's like a weird fun house where you go one way and then you try to go the other way and somehow you wind up back where you started even though you thought you were heading outward. That's what being inside the horizon of a black hole would be like. Which I think is actually much creepier and more entertaining than the traditional science fiction view of this. Now, the horizon plays a very important role in that if you're outside the horizon of a black hole, nothing from inside the black hole can ever reach you. And that means that you can't explore the singularity. We kind of like to because it looks like a weird, interesting thing to study. But you don't really have access to it. There's no experiment you can run that will tell you anything about the singularity. All you know is that there's this horizon, and once stuff falls in past it, it's gone. That's really all you as an experimenter outside the horizon can ever say. This is called cosmic censorship. It's one of the basic principles of general relativity that you shouldn't have a singularity without a horizon. That whenever there's a weird, bad place that we don't really understand, it's hidden behind one of these cloaks. And we never actually have to deal with it as scientists. Now, one of the most famous features of black holes is called Hawking radiation. Classically, I've just told you that nothing can escape the horizon of a black hole. Not quite true. Classically, this is true, but quantum mechanically, there's a bit of a caveat. We know that in the vacuum, as we've discussed, particle-antiparticle pairs are always popping into existence and then popping out of existence again. They create, then they annihilate, and they don't really do anything. They just pop into existence and pop out, and nothing really happens. But if this happens near a black hole, it can have a very important effect. Because suppose this pair is created right near the horizon, and it happens that one of the virtual particles is inside the horizon, and the other is outside the horizon. Well, if it stays that way, then these particles can never annihilate again. They don't have that opportunity. Now, right now, suppose they just popped into existence. They're really just sort of still virtual particles. They don't have definite mass, they don't have definite energy, they don't have definite anything because nobody's measured them. But if one of them falls into the black hole and the other one comes out, and we measure the one that comes out, suddenly that guy has a very real mass and a very real energy. It has some positive, definite energy that we just measured. Well, in order to account for this, we need energy to be conserved at this point. What do we say? Well, one popular interpretation is the particle that fell into the black hole has negative energy. And this is a problematic thing to say that I'm not sure I really understand. But what I do know is that there is a way of measuring the total amount of energy that's behind the horizon. The total amount of energy that's behind the horizon is just the mass of the black hole. That's all it is. And I can measure that by measuring how much I'm attracted to the black hole out here, even past the horizon. So I can measure that. And what turns out to be true is that the total amount of energy behind the horizon decreases by some incremental amount. The particle-virtual particle pair are created. Nothing's definite yet. One of them falls into the horizon, one of them falls out. The guy who comes out, we measure it. It has some definite positive energy. The energy behind the horizon some incremental amount so that conservation of energy is still followed. And what we say is that the black hole has radiated away a small amount of its mass. This is called pocket radiation. It's a bit tricky, but it really comes down to the fact that we never directly measure the particle that's inside the horizon, and because of that, it gets to do lots of strange things. Yes?
Couldn't the negative virtual particle fall in instead of the positive one, so that there'd be a net gain?
Remember that neither one of them is negative or positive. They both have indefinite energy until one of them is measured. The one that's measured is always the one that comes out. And once it's measured, it has to have positive energy.
Suppose particles...
It's like quantum, remember quantum mechanically, when an electron can have any spin, indefinite spin, but the moment you measure it, it has either spin up or spin down? It's like that. The virtual particle has indefinite energy. It can have anything until you measure it. But the only values that are possible for us to measure are positive.
Well, before there were humans, they were never measured.
By measure, that's a bit of a tricky philosophical question, what you mean by measured. But really, most scientists think of measured as interacting with the outside world, whether it be with a human or just with the rest of the universe. Yes?
The virtual fluctuations occur for every part of the magnetic field. So what about the other conservation laws, charge, straight, color, and what happens to that?
Good point. I was about to mention the fact that, according to general relativity, a black hole is an extremely simple object. What's inside the horizon is described by very few numbers. One of these numbers is mass. However, it also has angular momentum, and it has charge, possibly, and it could conceivably have color or strangeness or whatnot. And you're right, if the particle that comes out is an electron, if it's a virtual electron, then in addition to the mass of the black hole decreasing by some small amount, its charge also has to increase. And that's fine. It's just, we impose these global conservation laws, but we never actually say the virtual particle now has a negative charge or positive charge. We just say the stuff behind the horizon has changed its charge by some increment. But it works just the same as the mass.
So it evaporates and disappears. It lost all its mass, which is a reason for its existence. This information, I know there's a big argument about what happens.
I'm getting there. I'll take one more right now, but then I should go on.
A moment ago, you said that you either had difficulty understanding something or didn't understand something relative to, I think I've understood you to say something about negative energy. Could you mention what the source of the difficulty is that you were troubled with?
It's not, all right, let's put it this way. Mechanics, that before I measure the energy of an object, it doesn't have any definite energy. That means that before I measure the energy of the particle, positive, negative, I don't know. Once the virtual particle has left the black hole and I measure it, it becomes an actual particle. It has positive energy. And by the conservation of energy, I know that whatever is behind the horizon has decreased its energy by some small amount. That isn't to say that I ever measured the particle that fell into the black hole and found it to have negative energy. I never measured it. It's inside the horizon. I can't. All I can say is that the net energy inside the horizon has decreased. I think this is where you were going. There's a bit of a problem with this picture. In particle physics, so far in the last 6 weeks, everything basically that I've ever described to you is a reversible process. And what I mean by that is that if I studied the process in nature and I videotaped it, and then I put the tape in backwards and I reversed it and I ran it backwards, you shouldn't know the difference. You shouldn't be able to say, that tape is backwards, that process is not allowed. Whatever I run forwards is equally possible backwards. This is one of the basic fundamental rules in quantum mechanics. However, what I have just described to you of this process of things falling into the black hole and then particles radiating out away from the black hole violates this. And the reason it does is, remember that the black hole is very, very simple. What's behind the horizon has mass, it has some charge, it has some angular momentum, and that's basically about it. It's an extremely simple object. And yet, which means that what's coming off the black hole, the Hawking radiation, only depends on a very few small numbers. The total mass of the black hole determines how much Hawking radiation is coming off of it, and the total charge of the black hole might affect what kind of Hawking radiation is coming off of it, and whatnot. But Hawking radiation is also very simple. There's not a lot of information there. There's not a lot of complexity there. On the other hand, you can have whatever you want fall into the black hole. We can toss a bunch of physics textbooks, the complete works of Shakespeare, and the Bible into the black hole. And where does that information go? Well, so we toss a bunch of stuff into the black hole, and then the black hole evaporates away. Well, we threw in a bunch of complicated stuff, and what we got out was extremely simple. Where did that complexity go? Where did that information go? It seems to have evaporated, and there's no way that we could film this process and then reverse the film and run it for you guys and have you guys not realize that I reversed the film. It's completely distinguishable. This is in conflict with the assumptions of quantum mechanics. This is called the information paradox, and it's the first problem with gravity that I'm going to name. This is a conflict between quantum mechanics and general relativity. Now, there's a thing that's been weighing on my conscience for the last couple of weeks. I've been lying to you all. It's a terrible thing. I do that, I lie. I've been saying that the total amount of energy in a system never matters, that all you ever measure is differences in energy. Well, this is true right up until the moment when you include gravity. And I want to talk about this. So, according to Newton, the gravitational force basically comes from mass. An object feels gravity when it is massive. However, we learned from Einstein in the very first lecture that mass is just one form of energy. It doesn't really make sense for gravity to have to do with mass and not with any other form of energy, because mass is just one form of energy. It's not even a particularly special form of energy. What it implies really is that it's not actually mass that gravity is reacting with, it's energy. Whenever you have some amount of energy in a space, that energy gravitates. And mass is just one example of this. In the classical world, the amount of energy in the sun is incredibly dominated by the mass of the sun. Most of the energy that the sun has is its mass energy. And because of that, we don't really notice it on a day-to-day basis. But the reality is that it's not the mass of the sun that's creating the gravitational field, it's its energy. All of its energy, not just its mass energy. And because of this, gravity is the one force that cares how much energy there is in a system. Not just about differences in energy, but about the total energy. And all of this time, I've been playing this game with what we call the vacuum. Oh, where's the energy level? It's here. Oh, no, it's here. It's here. Doesn't matter. All we care about are differences. Now it does. How much energy what we call the vacuum has in it affects how it interacts with the force of gravity. And it has an energy density that comes from various places. It comes, for example, from the Higgs field. We said that the Higgs field had this potential energy like this, and we live down here at some negative energy density. Well, that's one source, but there's also, for example, every single field has these particle-antiparticle pairs floating in and out of existence, and that creates some background energy level. Come from the quantum fluctuations creating some background energy level. There are a whole bunch of sources. And all of them together mean that the vacuum has some natural energy density, which is also called the cosmological constant. And we suddenly need to care about it. We need to understand what its effects are. Now, for unfortunate historical reasons, if the vacuum has positive energy density, then we say that the cosmological constant is negative. And if the vacuum has a negative energy density, then we say that the cosmological constant is positive. That's just one of those historical accidents. It's like Benjamin Franklin deciding that the electron is going to be negatively charged and driving all of the electrical engineers for the next 200 years on the wall. So let's talk about the cosmological constant. And let's talk a little bit about the way the universe expands. Forget about the cosmological constant. Suppose we just have a normal universe with some mass in it. We know that it is expanding, and we know this because we look at stars that are far away, and we see that they are receding from us. We see that the vast majority of stuff out there in the universe is flying away from us. And furthermore, the further away it is, the faster it's flying away from us. And this tells us that the universe is expanding. It's an observational fact. We know this. Now, barring the cosmological constant, the old understanding was that the only force that really acts on the scales of the universe is gravity, because when we're talking about planets and galaxies and whatnot, things are essentially electrically neutral. They're color neutral. They don't, have a strong, weak interaction. And because of that, the main effect is always going to be gravity. And gravity, for all normal matter, always attracts, because all normal matter has positive energy. And what this means is the only thing that affects this expansion is that things tend to want to attract each other, which means that the expansion should be decelerating. It's flying apart, but the stuff in the universe tends to want to stick together, so this deceleration is slowing down over time. That's the old understanding. Now, depending on how much matter there is in the universe, how dense stuff in the universe is, this could mean different things. We can certainly imagine that if there was a whole lot of mass in the universe, then the expansion would slow down until it finally stopped, and then everything would fall in and crunch again. Or we could imagine that if there really wasn't a lot of matter, then maybe the acceleration then maybe the expansion gradually decreases in speed, but it never really stops, and the universe just expands forever. Or maybe we have just exactly the right amount of stuff, and it just sort of asymptotes out to some finite amount, and then it stops. Well, we describe the amount of matter there is in the universe, this density, by omega, and we say omega is defined so that if omega is equal to 1, we have this perfect picture where the universe neither keeps expanding forever nor crunches. That's omega equals 1 up here. Well, what about this vacuum energy density, this cosmological constant? If the vacuum energy density is positive, which means the cosmological constant is negative, then this picture isn't really all that different. You still just have stuff that's going to gravitationally attract, and the expansion of the universe is going to slow. But if the cosmological constant is positive, what does it mean that the vacuum energy is negative? What is the effect of this? Well, there's really only one effect of this, and that's that this expansion can actually accelerate. This negative energy that's in the vacuum, its only effect that we ever see is that it's sort of repulsive gravity. It tends to want to fly apart from itself. And that means that the universe can accelerate in its expansion. Now, if I was giving this lecture, I don't know, 10 years ago, maybe 11 or 12 years ago if I want to be safe, most people would have assumed that the cosmological constant didn't exist. However, there have been a set of measurements that have told us about, and we define the density of this vacuum energy, the cosmological constant density, by a similar parameter that goes between 0 and 1 on this little graph that I have. There have been a series of experiments that have told us about these quantities. The first one, and the one that came out while I was still an undergraduate, and first getting excited about physics, and this was probably the most important thing that was discovered in the years that I was an undergraduate student, is that if you actually look out and measure how fast things are receding from us, and then you look at further things and you measure how fast they're receding, and so on, what you find is that it's an observed fact that the universe's expansion is accelerating. This is pretty well known at this point. And this basically means that there has to be some positive cosmological constant, because that's the only thing that can repulse it, at those distance scales. You need something that creates repulsive gravity, and a positive cosmological constant is really the only thing that can do it. Now, if you look at this band is a range of possible values for the amount of matter versus the amount of cosmological constant in the universe. The fact that the universe is accelerating and the amount by which it is accelerating in its expansion gives you this band. Basically, we know that the universe expansion is accelerating, so if there's no matter in the universe, then that means there must be a certain amount of cosmological constant. If there's some amount of ordinary matter that tends to want to make it contract, that means there must be still more cosmological constant, and so on. So you create a band in this range that says, we know that whatever the amount of matter is in the universe, the amount of cosmological constant must be enough to compensate for it and cause the universe to be expanding at an accelerating rate. The other thing that came out, and this happened really while I was a graduate student, is that matter and vacuum energy also cause the universe to curve. Like I said, general relativity tells us that this stuff creates a curvature in space, and you can measure the curvature of space. These are experiments having to do with the cosmic microwave background, which I unfortunately don't have a lot of time to talk about. But they give you a second constraint that looks like this. And then you can also just flat out measure the amount of ordinary matter in the universe. You can measure it by looking at how much stuff there is out there, how much luminesces, and you can measure the amount of dark matter by looking at how fast galaxies are rotating and figure out how much mass there must be in them from basic Newtonian physics. And they've measured what omega matter is, and they found it to be around 0.3. And you can see that all of these experiments together conspire to tell us that there is some positive cosmological constant. And it's about omega lambda equals 0.7. And any two of these experiments would have told us this, but the third one makes it really clear that we're on the right track, that we're not wrong. Now, why is this a problem for us? It's a problem because these measurements imply a very small positive cosmological constant. That's a very small amount of negative energy density. the electron and its field, and we measure the vacuum energy density that comes from that, we get a number that is 120 orders of magnitude larger than the observed value. Now that's just one possible source. But what it means is that if we added up all the sources, then they all have to cancel out to 120 decimal places to give us what's observed. This is really strange. And not only do they cancel out to 120 decimal places, they don't cancel beyond that. It's not like there's some fundamental law of nature requiring it to be zero, because it's not zero. We could understand if it was zero. What we have instead is that it's bizarrely tiny. And this is called the cosmological constant problem. It's the second problem with gravity. Now, the third problem with gravity is traditional quantum theories assume that particles are point-like objects. And most of the time, we don't really worry too much about this because we're not very close to them. But suppose we start getting really, really close in to an electron, say. What this really implies is that there's some finite amount of mass or charge or energy or what have you concentrated in basically no amount of space. This is weird when you really start to think about it. This is a problem. Now, we don't usually have to worry about this, and the reason has to do with what I've mentioned earlier is quantum shielding. We never actually have to deal with the electron by itself, because we also have these electron-positron virtual pairs floating in and out of existence, and they can interact with the electron via virtual photons. And if I'm out here, then what I see is not the bare electron, but some weird composite object, and I never really have to deal with the bare electron. And in most cases, it's fine for us so long as it's fine for us to study the system at low energies and avoid, for now, the problems with high energies or short distance scales that are implicit in this bare object maybe not making a lot of sense. Well, there's always a problem with this at high energies, but usually it's okay to say, well, something else happens at high energies, but we don't really care. It doesn't affect what happens at low energies, and that's okay. It turns out that gravity is worse than this. It is completely impossible to separate the low energy quantum mechanical behavior of gravity from its high energy bad behavior. This is what people usually mean when they say that gravity can't be quantized. Now, this is the problem that string theory was really almost tailor-made to solve. A lot of people think of string theory as this very strange, weird, crazy, spooky idea, but at the end of the day, it's almost childlike in its naivety, because, well, you have this problem with objects being point-like, and all this mass is concentrated in this tiny volume of space, and that creates some weird singular thing and we don't know how to deal with it. Well, how can we deal with it? Let's assume that the object is not actually point-like. Let's give it some length. It's the dumbest, most basic assumption you could possibly make to solve the problem. So you make the object little one-dimensional strings instead, and what this does is it introduces a natural length into the problem, and that length is the length of the string itself. So we take an interaction between a couple of electrons where they exchange a photon, and what we really replace it with is we have a string coming in and a string going out, and a string coming in and a string going out, and it's just this, blobby, spread out interaction. And saying that these guys aren't fundamental either. They have little quarks inside them. And the quarks come in different types, and the way the quarks are arranged give us these patterns. This is the old paradigm. And the first question you should be asking is, well, what's inside a quark? String theory gives us a new paradigm for this. It says it's not necessarily a bunch of smaller objects. That's not the only way that you can get patterns and structure. Maybe it's just one extended thing, and the shape of that extended thing gives you different particles. For example, suppose you have a little string, and one of them is shaped like this. Well, from a distance, that looks like some particle of type A, and you have a different shaped string over here, and from a distance, that looks like particle B. This gives us a different way of imagining what's inside a quark and what makes an up quark different from a down quark, for example. Now, what about the masses of these particles? We know that the mass of an object is really just its energy when it's at rest. And if an object is not point-like, but it has some shape, some structure to it, then we want to think of this as being the internal energy of this shape. So this string can have waves on it, and the more waves are on it, the more wiggles, the more energetic the string is, the more internal energy there is. And what this means is that if you have a string that doesn't have any waves on it, it has some small amount of mass. If you have a string that has some internal energy, it creates a slightly bigger mass. If you have a string with a little bit more, then it creates a bit more. And what you get is a pattern of increasing mass. So one little string can account for a whole bunch of different particles with different masses because the shape of the string generates different masses. The same could be true of spins. Now, we've said that the spin of a particle was its intrinsic angular momentum. Well, if the particle isn't just some point-like thing, but is some, structured object that we can understand, then maybe this intrinsic angular momentum is the angular momentum implied in the motion of the string itself. So here I pictured a little closed string instead of a little open string. They're both possible. I have some waves on the string, little wiggles, and the waves are traveling around the string. And you can see that as I go down the line, I have more waves traveling around the string. And because of that, the little object inside that we can look at has more angular momentum. And what that creates is a variety of different amounts of spin. So this particle here with a whole bunch of waves traveling in circles, this has a lot more spin than this guy down here. And it's because the actual string itself, when you look at it, has more spin. We also talked a couple of weeks ago about this idea of unifying forces. What does gravity have to say about this? Well, or what does string theory have to say about this? Well, if we expect string theory to describe the real world, then in particular we want certain strings to play the roles of the mediator particles. We want a particular arrangement of a string to be a photon. And the exchange of that particular string explains the electromagnetic force then. Well, it turns out that, in fact, string theory is very, very good at this one. Little open strings, it turns out, can be created so that they have no net mass and they have spin 1, which implies that they are essentially like gluons or photons. And little closed strings can be created so that they have no net mass and that they are spin 2. And those are little gravitons. And under this picture, the whole story of these virtual particles of forces being exchanged is replaced by just string exchanges string, always and forever. And it's a very pretty, simplistic unification picture. cosmological constant problem, and I gave you this weird high energy behavior problem, and I really only solved the third one with string theory. What do strings have to do with the black hole information paradox? Well, what most people now assume is the solution to the information paradox is that this idea that the black hole, that general relativity gives, that the black hole is such a very simple object and it's described by very few numbers. Well, everything that's inside the horizon is described by just 3 or 4 different numbers. A lot of scientists now think that that's wrong. That in fact what the black hole is can be described as a more complicated object. And you could think of it as just a whole bunch of strings. All of the strings, because everything is strings, all of the strings that fall into the black hole together describe what the black hole is. Well, that's very easy for me to say. Can it actually be done? Can we write down mathematically a black hole in terms of strings, in terms of these internal states, and reconcile it with general relativity? Yes, in a couple of extremely special cases. This has been done only for very certain special cases. The general understanding is not fully worked out. So we think that string theory can solve this problem, but we haven't done it yet. What about the cosmological constant? Well, one of the most famous drawbacks to string theory is that it doesn't actually work in 3 spatial dimensions and 1 time dimension, which is what we have in the real world around us. It seems to only make sense in a particular set number of space-time dimensions. Usually this is 10 for string theory. There's an extension called M theory for which it's 11. Whatever it is, it's larger than 4. And we don't really know what to do with this. Well, I'm going to talk a lot more about this next week, and we can think of this as a little bit of a preview. What happens is that the other number of dimensions get wrapped up somehow in circles or spheres or donuts somehow. There are lots of different ways of doing this, and depending on how these extra dimensions are wrapped up, you get different patterns of particles and forces in the 4-dimensional world that you see. So the world that we have has a particular set of particles and forces, and this should be created by a very specific way of wrapping up the extra dimensions. We don't know exactly how to do this. What we do know is that depending on how you do this wrapping up, you get a different value for the vacuum energy. And so the hope, and this is a lot more wishy-washy than the solution to the black holes, which we really think we have a pretty good understanding of, is that maybe this might someday explain the observed cosmological constant. If we could just work out exactly how these extra dimensions are wrapped up, then maybe we could also explain why we get the observed cosmological constant. So, I want to summarize. I'm running a little bit over today. Gravity is different from the other forces, and the main reason that it's different is because the quantity that describes how much a force interacts with gravity is the same as the quantity that describes how much force is needed to accelerate it by a certain amount. Gravitational mass is the same as inertial mass. And this leads to the interpretation of gravity as curving space. Black holes are a prediction of this, and the Hawking radiation that comes from black holes seems to be an irreversible process, which is in conflict with quantum mechanics. If you assume that the principles of general relativity are absolute and the principles of quantum mechanics are absolute, then you can't solve this problem. One of the two has to give. Gravity interacts with the vacuum energy, unlike any of the other forces, and observation shows the cosmological constant to be positive and small. The vacuum energy density is negative and small. Gravity quantization breaks down at high energies in a way that is naturally solved by string theory. String theory is the simplest possible solution we could imagine to this problem. strings vibrating in a variety of different ways give rise to particles of different masses and spins, including gravitons and photons, which gives string theory a way of explaining all of the forces of nature. Finally, strings may solve the black hole and cosmological constants problems as well, but we don't yet have all of the answers.
Is the Higgs particle theory consistent with string theory?
Yes. The Higgs particle would just be another string, a particular internal structure. We have never observed a fundamental scalar particle. If we observe the Higgs particle, it will be the only observed scalar particle. However, most ideas of string theory assume that there are possibly more massive particles that are also scalars.
That's
Yes. You're talking about a different idea of string theory that I will talk a lot more about in the last week. It's almost orthogonal to this idea of string theory. Yeah.
Can
Yeah.
you repeat the questions? We couldn't hear what he said.
Sorry?
We couldn't hear what he said. Could you?
He was asking about the idea, there's an idea that I'm going to talk about in the last week of strings being an alternate description to mesons. Mesons are a pair of a quark and an anti-quark, and this idea that I described where you pull them apart and you create two mesons can also be understood as picturing the meson itself as a string rather than the quarks as strings. And that's kind of an orthogonal idea to what I was talking about today, and I'll talk a little bit more about it in 2 weeks. Yes?
Two questions. One, about how long has string theory been around? And two, when you say, well, we haven't figured out how to prove this yet, is that, am I correct, that that's analogous to there were observations of these subatomic particles in experiments, and then people produced the mathematics, which showed that was correct?
It's
Or they did
actually,
sometimes math first, sometimes
okay.
experiment first?
So string theory's origins are in the late 1960s, and they are, in fact, the origins of string theory are in this alternate idea of strings as a description of mesons. The answer to your second question is, I would say it's actually not really analogous to this, because whereas before, historically, what's happened is you've done some experiment, you've come up with some measurement, and then you've tried to explain this measurement by creating a physical theory. What we have in the case of string theory is, in some ways, fundamentally different. What we have is not really a measurement we can't explain, so much as it is conflicts between the theories that we have. We have quantum mechanics, which seems to work very well, and we have general relativity, which seems to work very well. And for some reason, when we try to assume that both are true, we find that they're kind of mutually exclusive. So string theory, rather than trying to explain a particular scientific experiment, is trying to explain a conflict between theories, which is really kind of different. And that's part of what makes string theory so difficult, because the energies that string effects are, come in at, we expect to be like the Planck energy, and that's much, much higher than any energies we can today explore in direct experiments. And that's one of the things that makes string theory so difficult, is that it's very difficult to get experimental information for us to work with. It's not fundamentally something that we can't experiment with. It's outside our technical abilities today. Yes?
I constantly am puzzled by the term singularity. Does that mean something that can't be measured? Is it not there? Is it there? And the other question is, somewhere I've read that there are many, many tiny black holes that come and go
Yes.
in the universe. It's full of tiny, tiny little black holes. So is this a lot of points which just don't exist, or what? I'm not quite familiar.
Okay, so, all right. The question was, first, can I say a little bit more about the word singularity and what I actually mean by it? And second of all, the questioner has read about the existence of tiny black holes and the possibility that that these actually do exist out there in the universe, and that maybe there are quite a lot of them. And what does this really imply? So the first answer is difficult, but if we again picture this curvature of space, what I mean by a singularity is a place where space is curved by an infinite amount. And that doesn't really make sense to us. And what saves us from this confusion is that this singularity is always hidden behind a horizon. You never actually see the singularity. All you see is there's a thing that's hidden behind the horizon. So you never directly have to deal with it, and you're never forced to deal with the fact that you don't understand it. String theory has the potential to possibly explain certain kinds of singularities, but this is, I think, maybe even more speculative than what I've already said. Now, the thing about tiny black holes is, again, what makes a black hole is not that it has a huge amount of mass, but that it has a lot of mass density. It's not the total amount of mass that creates a black hole, it's having that mass inside a small amount of space. It's definitely possible to create this using just a few particles. And in fact, this is one of the things that they're looking for at the LHC. So for example, suppose we have particle A, and here we have particle B, and they're flying at each other, and suppose we give them so much energy that they pass so close together that they're actually inside their collective horizon. Well then, they are a black hole. It's just two particles, but it's a black hole. And what happens to these tiny black holes is that they Hawking radiate away almost immediately. You get these virtual particles that become real particles, and what's actually observed at the LHC is not there's a black hole sitting in my machine, but we had two particles, they came together, they formed some object, and then that object decayed into some other objects. Well, that's not too terribly different from any other particle, particle interaction. However, what's true about the little tiny black holes is that the pattern of decay is very, very distinctive. So what they say is that if there is black hole creation at the LHC, we'll know it because it's hard to miss experimentally. They'll see it and they'll say, that looks like Hawking radiation. It doesn't look like anything else. We must have made a black hole. Yes?
Yes, the rationalization of mass being the energy of the string vibrating,
Yes.
that would mean that each additional step would be proportional, and so you wouldn't be able to explain, how do they explain the differences in mass being so arbitrary?
Strange?
Yes.
I'll talk a little bit more about that next week. Part of it has to do with these extra dimensions and how they get wrapped up. You're right, if we had just sort of empty space and, tried to create these strings, then you would get a very regular pattern of masses. But the compactifications of the extra dimensions and whatnot can change this pattern.
How many ways are there doing that?
More than there are graduate students to study this. Only if somebody wants to hire a graduate student for every one of them. Yes, go ahead.
If you had a dense enough particle, wouldn't it be a black hole by itself?
Yes. Usually, a particle, there's a quantum mechanical uncertainty in where a particle is. It's described by a wave rather than being this particle and it's right here. And usually that wave is big enough so that it's effectively like that mass is spread out over an amount of space, and so it's not a black hole. But it is certainly possible that you could you could give a particle enough energy that it would in itself be a black hole. You're right. Go ahead.
Are you going to have a chance in the next couple of talks to talk about the criticisms that are made of string theory and where those folks are going?
I'm not sure precisely which criticisms you mean.
Or do I?
My usual view of there's been a couple of widely publicized critics recently.
That's the ones.
A lot of their arguments about the problems with string theory have validity. The problem that I have with these guys is that the alternate theories that they propose are worse. As problematic as string theory is, and most of its problems come from the fact that most stringy effects occur at such high energies we can't really probe them. Alternate ideas such as loop quantum gravity have more problems. They also can't be explored directly, and plus, at least string theory is consistent with what we know. String theory encapsulates in it classical gravity and general relativity, and has the potential to create photons and gluons and explain the strong and electromagnetic forces. And string theory has the potential to describe the real world. As far as I know, nobody's ever been able to find a way to make loop quantum gravity even consistent with basic special relativity. I mean, that's a problem. When you're creating a new physical theory, you want it at low energies to be consistent with what we already know. You don't want it to predict that the cars outside are going to turn into pink elephants. It has to be consistent with the world we know at the energies that we're familiar with. And the problem with most of the alternatives to string theory is that they're not. Yes?
To me, when I'm listening to you just now, it's about concept, right? In the case of the point particle, you talked about a point, that's a concept. In your case now, string is the concept, fundamental concept from which everything.
Yeah.
Is that true?
Yeah. Yes?
Have gravitons been observed?
No, not directly. Yes? as it accelerates around you, which, you know, if you then picture the spaceship getting bigger and bigger and bigger until it disappears, is just being in empty space. The effect of being in free fall, that is, falling naturally under the effect of gravity, that is indistinguishable from being in empty space, unaffected by any force of gravity. Those are completely different situations.
And so when I'm accelerated in a jet airplane, this is a subjective sensation that I can actually feel. It seems to me to be different than what you say is my sensory experience of being attached to the floor because of the acceleration of gravity.
Well, if you're in a jet airplane, then you're being accelerated, you're being pushed towards the back of the seat, you're also being pushed down by gravity. And there's some net effect that you're probably being pushed kind of at an angle into the seat. That's what you really feel. And that, in net, is the same thing as being in empty space with the rocket like this, or being in a gravitational field that points exactly in this direction.
What I'm trying to get at is there's some, like, a background experience, subjective sensory experience that we attribute to gravity, which we sort of filter out of our consciousness, and we only subjectively feel the experience of additional force. Does that make sense?
I would say no. I mean, I can definitely run an experiment